Okay, so this section of your book basically focuses on rational exponents. These are rational, okay, that you already know. Those are rational numbers as well, but remember, a rational number means it can be written as a fraction, so it could be more complicated than what you see here, okay? So it's basically looking at something that's in this form in the exponent, all right? And so here's how it works. If I have a to this fraction power, okay, remember the rules of exponents. This means technically we could rewrite this like this, okay? Is everybody okay with the fact that having this one fraction is the same as having a to this power and then to this power, because exponent rules would dictate that we would multiply these powers together? If we multiply m times 1 over n, we would get m over n, okay? And what that means to me is this. That means the numerator acts like every exponent that I would expect it to act like, okay? It's doing what an exponent normally does. That's how I'm going to see that. The denominator is what's different, okay? And when you see something like that 1 over n, it means this. It means there's really a radical over a, and the index of the radical is whatever the number that is there for n. And then the m, like we said, is just like the normal power. So this means if I saw something like 8 to the 2/3 power, the way I'm thinking about that in my head is kind of two pieces of the exponent. That 8 is being raised to the 1/3 power, but it's also being squared. Okay, I know how to deal with squaring. The 1/3 is the part that I really have to process right now. And when I see an exponent like 1/3, 1/4, 1/2, I want to immediately think radical, okay? So that means this is 8 underneath a radical, and that radical has an index of 3, okay? So 8 to the 1/3 power is the same thing as asking the cube root of 8. Okay, the cube root of 8 is 2, and 2 squared would be 4. So 8 to the 2/3 power is the same thing as 4. Sometimes we can calculate them simply, and sometimes we can't. It kind of depends on the radical. If this was like a 4th root of 8, it wouldn't have been as simple for me to finish this, right? It would have been more complicated. So it just kind of depends. Is that okay with everybody when you see a fraction exponent now? So notice what exponents don't do. We can never get 0. Do you notice that there's no exponent that has the power to turn the base into 0? Okay. And we don't get negatives. When we use negative exponents, we get reciprocals. When we use fraction exponents, we get radicals. There's no exponent that has the power to make something that was previously positive into a negative. So make sure that you're like keeping straight those exponent rules, because they're going to come in play at the beginning of second semester. Okay. All right, the properties of the exponents are all the same properties that you had before. Okay, they're no different. So this is just a reminder. If I have two quantities multiplying together, they have the same base, and then they have exponents, I can add the exponents. Okay, here I can multiply the exponents. Here the exponent applies to both of the bases. So those are all the same exponent rules that you've seen before. We can do those same things when the exponent is a fraction. All right, so that's a reminder. That's straight from your textbook. So you guys can look there. All right, so simplifying expressions. Here's why it's useful. So you might think we already have radicals. Why would we choose to write it a different way? Knowing that these two things have this relationship, sometimes when you look at something in radical form, you're like, I can't do anything with it. But if you rewrite it in exponent form, because you know a lot of exponent rules, just rewriting it in that way allows you to see different things that you can do with it, okay? So the first one is kind of what we were just talking about. Just understanding that 625 to the 1/4 power means the same thing as the 4th root of 625. So 625 is 25 times 25. If you didn't know that, you would just start breaking it down with 5s. You should be able to tell that 5 goes into it, okay? And that you would eventually see 4 5s go into it. So you would be able to get that value. All right, and then sorry about the next part. These little boxes should be multiplication signs. Sometimes when the PDF converts, depending on the equation program we used, it doesn't always work right. All right, so notice the next one has 12 to a power times 2 to a power. Oops, sorry. And those don't have the same base. So if it was 12 to a power times 12 to another power, I would keep the 12 and I would just add up the powers. That's what my basic exponent rules say. Here, okay, I can't do that, but I'm going to do it two ways so that you understand. This is saying the square root of 12 times the square root of 2. So you can make that connection back to what you know before, and then you can see that you can do something with this to combine these together. The other way to think about it with exponent rules is since they have the same exponent, that they both have a 1/2 on them, you could rewrite this in exponent form as 12 times 2 and all of that raised to the 1/2 power. Okay. Either way, whether you go from here with the exponent form or here with the radical form, you're looking at the square root of 24 as what you have to simplify. Okay. And then the largest perfect square in the square root of 24 is 4. And so then that's going to be 2 rad 6. So a lot of rewriting shows up in this unit, and that's kind of like a, you guys will probably laugh when I say it this way, but like a creative math thing. Like it's not procedural. You can't memorize like every time it looks like this, I do this. You just have to know some properties and recognize like, oh, I could rewrite this way, I could rewrite this way, and whatever sits best with you to kind of see how to get through that. All right, and then we kind of see the same thing here with part C. Again, you could think of this as the cube root of 12 times the cube root of 8. Or you can think about it as 12 times 8 to the 1/3 power. Okay. Either way, you're doing the cube root of 96 in these problems. Okay. I kind of think it's silly to write it as 96 because then I just have to break it back down. And I'm not super great with 96, so I'm going to call it 12 times 8. 8 is a perfect cube. So when you look at it this way, you might have recognized that right away. So the cube root of 8 is 2. And then are there any perfect cubes in 12? Or when I break 12 down, if perfect cubes aren't as easy for you as perfect squares, think about breaking 12 down. When you break it down to its prime factors, do you get 3 of the same thing? Okay, and we don't. So that's then the best way we could do this. In exponent form, just so you guys know, if you saw these in exponent form, these things would be written like this. This is the other way to write them now that we understand that fraction exponents mean the same thing as radicals. And do you guys notice that I'm either going to put this symbol or put the 12 in parentheses because this exponent only applies to the 12 here because it was the only thing left underneath the radical. I want to make sure that it's not seemed like the 12 and the 2 are grouped together. Okay. All right. Any questions on the general idea of how to use the fraction exponents? Okay. All right. So this gets a little bit tricky, not going to lie. All right. So we're going to just do a lot of rewriting today. But before we do that, there is an idea of simplifying that we have to be really, really careful of. So normally, when we simplify radicals, okay, we always think of just taking as much out of the radical as you can. But now that you're studying things bigger than square roots, there's more things to simplify. So when you simplify a radical, yes, you want to take out as many factors as possible. But there's also another aspect that we've never really thought of, and that is we want to write it in a way that the index is the smallest possible value. Okay. So I'll show you guys what I mean by that. So let's see, let's say I want to do the 4th root of 9, okay? Does 9 have a 4th root? Does it have 4 of the same factors? No. So before today, we would say that that's the simplest form because you guys have always been doing this, right? Taking out whatever factors you can from the radical. But what we've been ignoring is that it would be simpler, if possible, to have a smaller index. So now when you're simplifying with numbers, with variables, it wouldn't kind of matter as much. you need to check two things. First, I check, can I take out 4 of the same factors out of 9? No, I can't. But now I'm not done. The next thing I have to check is 4th root of 9 really written the simplest way? Or is the 4th root of 9 a different root of a different number? Like, are there two things that are equal to each other where the index is something smaller than 4? Okay, so here's how I would check that. The first thing I would ask myself is, can I rewrite 9 in a different way as a power of another number? If not, I'm done. Okay, so if this is like the 4th root of 5, 5 doesn't have 4 of the same factors. Is 5 a power of anything other than 5? No. This one is already in simplest form. Okay, this is in simplest form. Now the 4th root of 9 is slightly different because though there aren't 4 of the same factors in 9, can 9 be written as a power of another number, something other than 9? Okay, so instead of 9 to the first power, it could be written as 3 squared, okay? That means there's another way I can express what's written up on the board. I could rewrite 9 as 3 squared, and it's hard for me to understand how that helps at all if I keep it under the radical. But think about writing your radical in exponent form. A 4th root means the same thing as having what exponent? A 1/4. And what happens when you're taking a power of a power? What exponent property, what effect does that have here? What happens with these exponents? What can we do with these two values? Multiply them, right? According to our exponent properties. When I multiply times 2 times 1/4, will it simplify? What is 2 times 1/4? 2/4, right? Does that simplify? Yes, it simplifies to be 1/2. So this is the same as 3 to the 2/4, but that's the same as 3 to the 1/2, which what would that look like when written as a radical? It's the square root of 3. What is simpler for somebody to try to understand in their head? The 4th root of 9 or the square root of 3? Like if I made you approximate a decimal and I gave a quiz where you had to tell me about what decimal you think this number is, do you think you'd have a better chance of getting it right if I ask you, what approximate decimal do you think represents square root of 3? Or if I ask you, what approximate decimal do you think represents the 4th root of 9? What do you think your head would feel a little bit better about? Square root of 3. So do we understand why that would be a simpler idea? The higher you make the index on the radical, the harder it is for us to kind of quantitatively understand how big that number is. So I know this seems really silly, but mathematically it makes sense that this would be a much simpler form and a much simpler way to view that number. So when you guys simplify something, when you leave an answer now and you're like, this is my final answer, I've done all the work to simplify this radical, I'm going to ask you to check something you didn't think about before, right? So we've already been doing this. The new thing I'm asking you to check is this. And the way that we're going to go through and check it is we're going to ask ourselves, can what's under the radical be written a different way? Do you see how with the 5, since it couldn't be written a different way, there was no need to try and go through this process? Okay. Now let's say that I tried to do like the 4th root of 8. Okay. So I'm done. I can't really take a 4th root of 8, but then I ask myself, can 8 be written as a power of a different number? Okay, it can. Instead of 8 to the first power, it could be written as 2 to the 3rd power, and the 4th root would be like an exponent of 1/4. Now, when these two multiply each other, this makes 2 to the power of 3/4. Does 3/4 simplify? No, meaning the 4 didn't change. If the 4 doesn't change, then I'm still going to have to use a 4 when I rewrite it back in radical form. And that means it didn't get simplified anymore. The 4th root of 8 was actually the simplest way for me to write it. Okay, so some of you will get really fast at this. Some of us will go for more of a procedural way. The first thing is obviously, can we write this at all in a different way? But really it's going to come down to when I write that, will it actually simplify with the exponent or not? If not, then I already have the simplest form. If yes, then there's probably another way for me to write it, and I should look at what that is. Okay, so now when you're simplifying radicals, you're not just taking stuff out of the radical, you're checking that the index is actually the smallest thing for that number value. Okay, is this all right with everybody? Simplifying now is heavier. Okay, all right, so let's look at a few. All right, so you guys actually go ahead and give these a try. So notice in part A, the first two are written with exponents, and it's asking you to write these in radical form. And then in part B, they're written with radicals, and it's asking you to write them in exponential form. So this is really just checking if you understand how to change the radical to an exponent or the exponent to a radical. So just rewriting right now. So you guys saw what a radical or an... All right, so rewriting the expressions in radical form. So Part A here had two expressions. They both had exponents, and I'm rewriting them in radical form. So first, I want you guys to understand this 4/5 as an exponent is only attached to the y, not to the -2, because there wasn't parentheses grouping them together. So the exponent is only attached to the base that's immediately next to it, unless there are parentheses indicating that it's attached to multiple bases. Okay. The 5 in the denominator means I'm going to interpret that as 5th root, and the 4 will remain the power. So you can write that two ways. The -2 shouldn't be any part of the radical because it didn't technically have the exponent on it. The y should definitely be under a 5th root, and then that power of 4 can actually be expressed two ways. The y can be raised to the 4th before you're taking the 5th root, or you can take the 5th root and raise the whole thing to the 4th power. Those are going to be equivalent. Okay. So questions on that one? All right, so the second one, there's one exponent on one base, which is d, okay, and it's a -3/2 power. So here's the part that's new, using the denominator and the fraction, and then here's me factoring out the entire other part. It's okay if you kept the negative with the 1/2, but the reason I like to not keep it with the 1/2 is the main mistake I see people make in exponent rules is that you guys tend to understand all the rules independently. So if I just give you a negative exponent, you know what to do. If I just give you a fraction exponent, you know what to do. All of a sudden I put them together, and you guys are like trying to process it all at once because you guys are very used to doing everything fast, and you tend to skip steps or make mistakes because you're like combining two steps together. So I like to separate the negative from the fraction more so that I do the exponent rules correctly. So the 1/2 means a square root, then this is still negative. Then remember, a negative exponent means that I'm using the reciprocal of this power. So that's why it's a 1/, the square root of d cubed. Okay. The square root of d cubed means either square root of d times square root of d times square root of d is one way to interpret it. Okay, two of those will make a d outside the radical with one left inside. Or if you thought about it as the cube being inside, we would simplify the radical like we've done in the previous lessons where there's one group of 2 and one left inside. So this is basically the answer. It's technically not written in a proper format if we're writing it with radicals and we have a radical in the denominator. So then to change my answer to be proper, I decided to multiply by an extra square root of d so that these will make a pair and no longer need the radical. But I have to do that in the numerator as well. So then in the numerator, I have rad d. In the denominator, I had a d outside the radical, and then these two square root of d's multiplied together made another d outside the radical, and d times d is where I'm getting the d squared. Okay. Questions on this example? Yeah.
Why couldn't you just stay with 1/d rad? Like,
I think I know what you're saying. Like this? Okay.
No, the one on the very bottom, like 1 divided by rad d.
Because this isn't, okay, so this one right here? Okay, two reasons. Number one, the square root of d cubed is not the simplest radical form. Like, so if I have this, whether I have it like this or like this, that is not the simplest radical form because there's 3 factors of d underneath a square root. So that radical can be simplified. So 1 factor of d comes out and 1 factor of d stays in. Reason number 2 why I couldn't keep it like this, it's considered improper to leave radicals in the denominator of our fraction because we have to have a rational denominator. Is that okay? Good question. Other questions that you guys have about this one? So looked super simple, right? This is kind of what I want us to wrap our heads around. Maybe it didn't look super simple, but like doesn't look like a ton of work, right? But you had to process multiple things. Exponent world, you have to process 2 difficult concepts, negative exponents and fraction exponents. Notice I separated them so that I could process them at separate times and I didn't mess them up. Second thing after that, like Dominic was asking about, I technically have an answer here, but then I have to understand all about simplifying radicals and how an answer should be written and make sure I can get through the rest of the problem from there. So like this was the new part. And then the rest of this was all about like, oh, this radical can be simplified. Oh, I shouldn't write something with an irrational number in the denominator of a fraction. Okay. Any more questions on those two, going from the exponent to the radical? All right, so let's look at it the other way. So a little less work here, okay? So from the radical to the exponent. So here in this first one, it's just important to note that all of this was underneath the radical. That's why you see me write parentheses like this. So you could write your answer like this, or you could say a to the 1/2, b to the 3/2. Okay? And then here, this was under the radical, and that radical would be like a 1/3 power. So we'd write that as w to the 2/3 power. And then random question for you guys. Would you be able to leave an answer like this? No, right? Why not? Stefan? Yeah, technically it's a radical still in the denominator. Do you guys understand that? You wrote it in a different way, but it means the same thing, which means it's not rational. So we have to rationalize it in our denominator. So just keep that in mind so that if one of these had been like 1/, we would have had to do some extra work in order to simplify that, okay? Remember what they mean all the time. All right, so we're going to work on the simplest form of these expressions. So part A here kind of proves the point about why even knowing that this connection mathematically is useful. Because sometimes I feel like we don't feel like it is. When I see a fraction exponent, I want to rewrite it as a radical because I'm more comfortable with radicals. So then like, why even write it that way to begin with? If we only worked with radicals and we looked at part A right now, we would feel like there's nothing we could do, right? We talked about this before. We can multiply radicals together, but how does that work when one's a cube root and one's a 6th root? That doesn't really work with any of our radical rules, okay? But if we rewrite this as a problem with exponents, this is the same as having 10 to the 1/6 power. Oops. I don't know why I chose to write parentheses on one and not on the other, sorry. Times 10 to the 1/3 power. And what do our exponent rules say that we can do in a situation like this? When you have 10 raised to 1 power times 10 raised to another power, what exponent rules can we apply here? How can we simplify this? Taylor? What's that? Yeah, we can add the 2. So we can keep the base of 10, and it will be to the power of 1/6 plus 1/3. So it seemed like in radical form, it was impossible to combine these together. But when I write it in exponent form, even though it might not be fun because they're fractions and now I have to add up fractions, there is a way to combine these together. So the common denominator when I'm doing 1/6 plus 1/3, I'm going to think about that as 1/6 plus 2/6, which comes out to be 3/6. So this is 10 to the power of 3/6. 3/6 is really just 1/2. Which means this is the square root of 10. We wouldn't have known that with our radicals, right? Would I have known that the 6th root of 10 times the cube root of 10 makes the square root of 10? I wouldn't have known that. But when I look at it this other way, I can see that connection. Okay, so that's kind of the purpose there. Can the square root of 10 be simplified any further? No, 10 can't be broken down. And this radical, I don't have to worry about making the index smaller because this is the smallest indexed radical, right? A square root has the smallest index. All right, part B. Yeah, sorry, Stefan.
Why wouldn't you like multiply the two? Like cutting them off?
Because remember our exponent rules say like, okay, so remember what these means if we go out and write them out in their most basic form. This means x squared, so that's x squared, times x cubed. So notice that x is still the base, right? And so x is still the base, but it now has a power of 5. So when I have this times this, I'm still using the base, the same number, not it multiplied by anything else. I'm just using it more times than I originally was. 2 times and then 3 more times, so 5 times total. Is that okay?
Yeah.
And whereas here I'm saying x squared times x squared times x squared, which then uses the previous rule and says, okay, I'm using the same base, so it will still be an x, but 2 plus 2 plus 2 would make 6, which so we just say just multiply these together. But in either of those situations, we don't change the base because we would technically still be using that base if we wrote it all out to multiply it. Is that okay?
Yeah.
All right, so part B doesn't have a lot of like operations to do. It literally just says the fourth root of 64. Okay. So first we would look for a fourth root. Does 64 have 4 of one thing inside of it, one factor? I don't know. Let's break it down and see. 8 and 8, 4 and 2, 2 and 2, 2 and 2. So it has a group of 4 2's and then 2 other 2's left over. So that group of 4 2's is a perfect fourth root that I can take outside of the radical. And then the group of 2 2's, those 2 2's would stay inside the radical multiplying each other, which would be 4. Okay? So I found 4 of the same factor, so I was able to simplify the radicand, the number underneath the radical. But now when it says simplify, our mind has to go 2 places, right? The place we've always gone, can I factor out some things from the radical? And then what do we have to look at now? We gotta look at the index, right? 4 is not the lowest possible index, so I wanna know, can I make it lower? So I look at the radicand, the number underneath the radical that's left. Can it be written a different way than how it's written here? So can 4 be written as something different than 4 to the first power? Yes. Okay, so it's worth checking out. It may or may not work, but it's worth checking out. So 4 power. So 4 can be written as 2 squared. And then my fourth root is like having a 1/4 power. Should I keep going? Am I going to have something here that can simplify? Yes, okay, this 4 will get reduced, and that's what I'm looking for when I'm trying to reduce the index of the radical. So this would be 2 to the 2/4, which is the same as 2 to the 1/2, which is square root of 2. So this process is telling me the fourth root of 4 is the same thing as the square root of 2. To write my answer in the simplest way, it's much simpler for people to comprehend this than it is to comprehend fourth root of 4. So I'm going to rewrite this as 2 rad 2. Okay, so do you understand 2 steps now to your simplification process? Like normally you would have just stopped right here and been like, found all the groups that can come out, done. And now you're just pausing for a minute and be like, can this be made lower? And notice the 2 questions I keep asking myself. First question, can this be rewritten as another power? Because the answer was yes, I went and did a little work. If the answer was no, I would have been satisfied with what I had here. Okay, so when the answer was yes and I went to do a little work, the first work was to rewrite it as that power and then keep going if something's going to cancel here to lower the index, right? So this denominator right here, if it's going to get lower. Jake?
Would it be wrong to say that it was 2 6 to the 4? Right?
2 6 to the 4th. No. So you would reduce 6 to the 4th. And so you'd have 2 to the 3/2 is what you would leave it as if you're writing it in exponent form. And so I'll tell you guys this when you're checking answers in the homework. They're a little bit unclear, but generally, if you're asking you to simplify, if they give it to you in radical form, you're going to see the answers written in radical form. And if they give it to you in exponent form, you're going to see the answers written in exponent form. Otherwise, it'll be like the beginning examples and it'll say like, rewrite in this form. But if it doesn't say that and it just says simplify, if it's a radical, they expect a radical kind of answer. If it's an exponent, they expect an exponent. On your test, we will say, because we don't want to leave any unclear or whatever. If we don't say, then we'll have to accept both types of answers. Otherwise, we'll say simplify, write your answer in simplest radical form. Simplify, write your answer with exponents, something like that. Is that okay for clarification? All right. So why don't you guys go ahead and try the stuff in example 4. It's just a matter, again, of interpreting the fractional exponent as what part would be the radical and what would contain the exponent. Now remember, the 5 could be thought of like this, or it could be thought of as 64 to the 5th power. Here's where I'm at. I don't know what 64 to the 5th power is, so I would rather break 64 to something much smaller if possible before I raise it to the 5th power. So that's why I made like the mental choice to write the 5th power outside instead of inside. Now, if you wrote it inside, you could write 5 64s and break those down and look for perfect cubes, and you should still get to the same place. Okay, there's not one right way to do it. Okay, so I knew the cube root of negative 64 was negative 4, and then that is what I was raising to the 5th power. Okay. For part 2, I first, like I said, wrote the decimal as a fraction, and then I separated the part that's new to me, having the denominator of this fraction and the rest of the exponent, so that I could interpret the 1/5 as a 5th root. Okay. And then remember, a negative exponent means it's like this quantity, but the reciprocal of it. So I wrote it as 1 over the 5th root of 32 to the 6th power. Okay. I knew the 5th root of 32. It's 2. Okay. So 1 over 2 to the 6th power, and 2 to the 6th power is 64. You don't have to do it in that order. Maybe you did the 5th root of 32 is 2. You knew to raise it to the 6th, and then you took the reciprocal. That's fine, but you have to use the root in there somewhere, the 6th power in there somewhere, and the fact that it was negative to write it as a reciprocal. Okay? Any questions about those? So again, if you took a different path but got where I got, you did fine, because there's a lot of rules that we're applying, and there's no order in which case you have to apply the exponent rules or the radical rules. Okay, it's not like order of operations. You just have to make sure you're applying all of them. So if each time we've done one of these today, one of the ones like this that had a negative and a fraction, if you kept messing it up, try separating it a little differently, or if you weren't separating it, try separating it so that you have the radical part and then the negative here, so that you do both exponent rules and that you don't skip over one or something like that. Okay. All right. The problems at the bottom, to write them in their simplest form. Just remember that because these are all multiplying each other and they're all being raised to this power, they are all getting that power. Okay. So this is going to be 9. It's now going to have a 3/2 power. Y is going to have a 3/2 power. The x is going to get the 3/2 power too, but technically the x already had an exponent on it. What was the exponent that I could write on x given this original part inside the parentheses? 1/2, because of the radical. And now it also gets a 3/2, which means it's going to multiply that value there. Okay. So 9 to the 3/2, remember, is like the square root of 9 being cubed. I know the square root of 9. It's 3, and 3 cubed is 27. Because this had a radical in it, they might want us to write it in a radical again. That might be how you see the answer. 27 is fine. It's outside a radical. It has no exponent power. If we want to put everything else underneath one radical, right now, the x would have to go under a 4th root, but the y would want to go under a square root. What do I need to do to their fraction exponents to get them under the same root? Okay, what would I want the exponents to have, the fractions? Emily? A common denominator. So instead of thinking of this as 3/2, I'm going to think of it as 6/4. So I could put them all underneath a radical, and from there I can see that 1y should come outside the radical, And 2 would be left. Now I know that this and this could simplify, but I don't want them to simplify because there's other things underneath the radical and I want to keep them all underneath one radical together. Okay? And then for the second, we'd have the same. So we're going to just distribute that negative 1/3 exponent to everything. And so we're going to have the cube root of 27, but that's to a negative 1 power. We have x to the negative 6/3 power and y to the negative 9/3 power. And both of those powers reduce. So cube root of 27 is 3, but it's still raised to the negative 1. Negative 6/3 is the same as negative 2. And negative 9/3 is the same as negative 3. So the nice thing here is that all the exponents worked out to be whole numbers. So no radicals are even involved in this problem, no fraction exponents left. The part you have to process is that each base here has a negative exponent on it, so they really want us to use the reciprocal of each of these. So I don't want 3, I want 1/3. I don't want it to multiply x squared, I want it to multiply 1 over x squared and 1 over y cubed. So this is really a fraction where the numerator is 1 and the denominator are all of these things being multiplied together. Okay? So main idea in these last couple of examples, when you have multiple bases in here, meaning they're all factors, they're all things being multiplied to each other, this exponent is applied to each of them. Okay? Then you can go and simplify each of them separately. If your final answer needs to be a radical, like it had radicals in it or it says to write it in a radical form, pay attention to what we did right here, common denominators, so you can put it under one radical. Okay? And if not, then just make sure you follow the exponent rules. Okay?